Hello everyone and welcome to our group presentations for digital signal processing. Today we're excited to walk you through the fast Fourier transform or FFT. The FFT is not a different mathematical transform from the discrete Fourier transform, but rather a highly efficient milestone algorithm designed to compute the exact same results with a fraction of the computational effort. Firstly, we'll look at the mathematical definition of the direct discrete Fourier transform. Computing an n-point DFT directly requires n squared complex multiplication and n multiplied n minus 1. This quadratic or O computational complex processes a massive botnet. For a standard 1024-point signal, we require over 1 million complex operations.
In 1965, Cooley and Turkey introduced a game-changing divide and conquer approach that recursively decomposed a large DFT of size n into a smaller subtransform. This slashes the computational complexity down to O(n) log base 2n. The practical implications are breathtaking. For 1024 points, the FFT is approximately 100 times faster. At 1 million points, it is 50,000 times faster. This dramatic increase the speed made real-time frequency analysis stable, practical, and high energy efficiency. There are two primary families of radix 2 FFT algorithms: decimation in time (DIT) and decimation in frequency (DIF). DIT FFT works by splitting the time domain input sequence xn into its even index and odd index sample. This exploits the symmetry of cosine wave and antisymmetry of sine wave to eliminate redundant calculation. In DIT, the input must be shuffled into a scrambled order to yield a naturally ordered frequency output. Conversely, DIF FFT accepts naturally ordered input but produces a bit reverse output.
The fundamental building block of the FFT is the butterfly structure, named after the wing-like crossing of a single flow path. In a radix 2 DIT butterfly, two complex numbers A and B are combined using the complex phase rotation factor called a Twiddle factor. Crucially, once the butterfly operation is performed on a pair complex number to produce a result, there is no need to save the input pairs. Hence, we can store the result in the same location as the input. Consequently, we require a fixed amount of storage, namely 2n storage register, in order to store the result. So because the operation is involution, it allows for high performance in place implementation that do not require additional memory allocation. This minimizes register allocation and eliminates the needs for extra buffer memory, which is vital for space constraint and better DSP hardware. A second important hardware observation is concerned with the order of the decimator input sequence. For an at-point signal, the input sequence must be stored in a very specific scrambled order. The spatial order is precisely the bit reversal permutation. By expressing the index n in binary form, the position in the decimator array is easily obtained by reading the binary representation in reverse order. For example, data point 3, which is 0, 1, 1, is placed in the position 1, 1, 0, which is reverse in the decimator array. While this shuffling lacks spatial memory locality can introduce memory access latency, it remains a necessary step to produce a perfectly sort order frequency output.
When implementing these butterflies in physical silicon like FPGAs, standard implementations can consume massive area and register. To optimize this, hardware designers use folding transformation, mapping multiple algorithm operations in the same column to a single physical butterfly functional unit. By performing register minimization using linear lifetime charts, an 8-point pipeline folder architecture can run only with 4 registers instead of 16. Pipeline architectures produce results very efficiently in less time with fewer slices on FPGAs, optimizing size, weight, and power of swap in modern radar and wireless chips. The FFT is a workhorse across many industries. First, in medical imaging, it is used with high-pass filtering to sharpen and enhance chest X-rays, making it easier to screen and distinguish bacterial pneumonia, viral pneumonia, and COVID-19 at early stages without heavy neural and network training. Second, in radar system, hardware FFT core processors offer DSP cores to compute millions of 1034-point FFTs per second, allowing low-power real-time match filtering. Finally, in 5G wireless communication, DFT spread or FDM uses FFTs to spread symbols across subcarriers, reducing the peak-to-average power ratio to save mobile battery life.
In this physical measurement system, we must deal with the real-world limitation. One major consideration is the assumption of periodicity. The FFT assumes that the input signal is periodic. If the signal does not align perfectly at the boundary of our sampling window, our boundary disconnect occurs, causing spectral leakage. This leakage signal energy into adjacent frequency bin distorting the spectrum. To mitigate this, smooth window functions such as ham or hamming are applied before the FFT to taper the signal towards zero at the boundary, suppressing side lobe at the cost of steady frequency restoration. Let's now solve our classroom tutorial problem step by step. We have given the input sequence xn, and in the part A, the DTFT is valued at omega equal to 0.25 pi. By expanding our complex exponential, we obtain 1 plus j 0.142, and the magnitude is 1.0824. For part B, we sample this spectrum using the 8-point DFT. The continuous frequency omega equal to 0.25 pi corresponding to the frequency k equal to 1. After 0, expanding our sequence to length 8, the DFT completion at k equal to 1 yields the exactly same complex value, demonstrating how the DFT sample the underlying continuous DTFT spectrum.
For part C, we compute the 4-point FFT using the DIT butterfly structures. Firstly, we split our input into even index samples, 1 and 1, and odd index samples, -1, -1. In stage 1, we perform 2-point DFTs. The even DFT GX use 2 and 0, and the odd DFT HK use -2 and 0. In stage 2, we combine them using the Twiddle factors W4 equal to 1 and W4 equal to -j. This combination yields our final 4-point frequency domain factor of xk equal to 0.0. The computational complexity for this 4-point radix 2 transform is exactly 4 complex multiplications and 8 additions. To conclude, Part D highlights the 3 key fast computation factors: divide and conquer decompositions, Twiddle symmetry, and periodicity. In Part E, we note that while radix 2 butterfly drastically reduce calculations, they suffer from a rigid power of 2 length constraint. If your raw data length is not a power of 2, zero padding must be used, which interpolates the spectrum but does not improve the true physical resolutions. In addition, memory bit reversal reordering adds special access overhead in VLSI hardware. Thank you very much for your time and attention.